All right, and hopefully the last video for the very first section of chapter 4 on vector spaces and subspaces. I've drawn this out, I've stretched it out because it's so important for where we want to go from here. Okay, so let's just do a summary. Hopefully everything that I'm about to say is understood at this point from the previous videos. So let's start. What is a vector space, right? Well, it's a set of vectors and a set of scalars with two operations: vector addition, scalar multiplication. With that, with those defined, there are 10 axioms that must hold to meet the condition to say that it is a vector space. What is a subspace? Well, it's the same in the sense that it's a set of vectors, set of scalars, two operations, two operators at vector addition, scalar multiplication, only now there's 3 axioms that must hold. Now, a couple things, just I want to make sure you hear this. So I'm going to read. Every subspace is a vector space. Now that might be confusing, but you can think of it, maybe I'll try an analogy. You can think about starting with a long piece of string and then making 2 cuts. Now you have a smaller piece of string. That smaller string would be a subset of the larger string. But I could make 2 more cuts, and then you would have a even smaller piece of string that would be a subset of the previous piece of string. I hope that makes sense. So every subspace is a vector space. And now that means, and also every vector space is a subspace. So that's important to know. That every subspace is a vector space and every vector space is a subspace, either of itself or some larger space. So you can actually be a vector space or a subspace of itself. Okay, the last bullet point here is the 0 subspace. Now that's one single point, right? The 0 vector. So the 0 subspace is simply the 0 vector of some vector space V. Okay. Let's practice a few more. These are not tricky, but they're made to, or they're designed to make sure that you have a pretty good understanding of your vocabulary to be able to answer them. Let me read. So, is R2, now remember R2 is just 2-dimensional space, is R2 a subspace of R3? Now I could ask the same question, I just wrote it both. I could also ask, is R1, a single line, a subspace of R2? Right? So we've already shown that R1 is a vector space. We've already shown that R2 is a vector space, and I could do the same for R3. So is R2 a subspace of R3? That is the question. And let me actually start with the answer. The answer is no. R2 is not a subspace of R3. In fact, R2 is not even a subset of R3. How do I make that more clear? every point in R2, right? Every point in R2 takes on the following form. The form that it takes looks like this. Every point in R3 takes on the following form. Do you notice that there's not, just structurally, these are not the same. Now, if you were intuitively, if you answered yes to that question, then here's what you were thinking. You were thinking about a very special subset of R3 that looked like this, right? This is, if you had answered yes before, you were thinking the answer would be yes. Here's what you were thinking. There's a special, I don't know why I write special. There's nothing really special about it, but I guess it's special to me. There's a special subset of R3 all right, there's that looks and acts just like R2. R2. All right, so there is a subset of R3 that it looks and acts exactly like R2. And what is that? It would be the case where you have X, Y, 0. Now that is a subset of R3. What this structurally cannot be a subset of R3, because by definition R3 must have, well, let's just say a length width height, right? Structurally the way we've set this up with just length width does not make any sense. So the answer was no, it was not a subspace. All right, now I tell you what, let me give you, I'm gonna read this to you, pause it, take 30 seconds to see if you can answer the question, and then press play. Ready? So look at the following graph, the following figure 8, and answer the question, is H, that's this line right here, right? Is H a subspace of vector space R2? Pause it, and I'll come back and I'll answer the question. All right. So what did you decide? If you're thinking, well, wait a minute, how do I do this? I don't have any points. I don't have any, if I don't have an equation of the line, how do I set up my axioms to be able to test this? Well, let me just ask it this way. Does that line go through the origin? No, it does not. That means there is no 0 vector. If there is no 0 vector, then by definition it is not a subspace. Does that make sense? I hope that makes sense. All right, last slide. All right, so let's review two. I'm going to have to erase this after I write them, but let's review two very important concepts from before the midterm. The concept of a linear combination, and the concept of the span of vectors. Okay, so I've already discussed these with you, so I'm going to erase this as soon as I'm done, but really quickly, do you remember linear combinations? So a linear combinations is just the sum of scalar multiples of vectors, right? So C sub 1, V sub 1, plus C sub 2, V sub 2. And for every vector. right? That's a linear combination. A linear combination. It's just the sum of some vectors that are scaled. Okay? Now, what is the span? What is the span of a set of vectors? Well, it's the set of all vectors right? The set of all vectors that can be written as linear combinations. All right, so two previous ideas. Now we're going to see how they play a role in subspaces, vector spaces. Ready? So I'm going to read example 10, and while I start example 10, I'm also going to unpack this what we call the subspace spanned by a set. Okay? Right, or sometimes it's referred to as, I'm not used to that, I'm used to the term generated, subspace generated. All right, so now let me start with example 10. So I do have to give myself a little bit of space by erasing those definitions. You can always rewind if you need to. All right, and I'll make this, well, let me just get my highlighter out. So for example 10, what are we given? We're given two vectors, v1 and v2. Okay, now we're not told if we're in two-dimensional space or three-dimensional space. That we're not told. We're just told that we have two vectors. So we're given two vectors that are in a vector space, V. With me? So you can think of it, they reached into a vector space and grabbed two vectors, and that's what we have. Now, we're going to say H is the span of those two vectors. So notice what I'm doing right here is what is that first? H is the span of those two vectors. So that would mean that H is written as follows. The span of two vectors, remember you have v1 and v2, those are the only vectors you have, and the only thing you're allowed to do when you're spanning is scale them and add them. H is the span of those two vectors. Now what is our job? Our job is to show that H is a subspace of V. So we should be able to show that H is a subspace of V. Let's start with the easiest one. Let's start with given H, is the zero vector in H? Let's start there. All right, so let me rewrite. So we have H is equal to C sub 1 multiplied by V sub 1 plus C sub 2 multiplied by V sub 2. And my only question is it possible for us to get to the zero vector from here? Well, of course, because all that would be required is that you choose weights that are zero, right? You can choose any scalars that you want. So, of course, in that scenario, we would have H is equal to 0 times V sub 1 plus 0 times V sub 2. In other words, H is equal to the zero vector, which is exactly what we would need for that first axiom. All right, now, the next axiom is, we'll start with, is H closed under addition. Okay, now, to be closed under addition, we're going to need two vectors and scalars. So the idea of, if you have u, I'm actually, yeah, so if you have u, let's write u is some vector, and then v is another vector. So let's see if we can set this up. Ready? Let's say that, let's start with the easy one. Let's say c sub 1 v sub 1 plus c sub 2 v sub 2. That's our first vector. All right, now I gotta choose another vector. Okay. Now I can't change v sub 1 or v sub 2. That I can't change. The only thing that I can change is the scalars that I attach to them. So we'll say c sub 3, c sub 4. I hope that makes sense. So this is these are two potential vectors, or I'm sorry, these are two vectors that are in our subspace H. Now, to have closure under addition, that would mean that u plus v must also be in H, right? So how can we think about this? Well, let's see if we can. How do we think about u plus v? So let me go ahead and write this as c sub 1 v sub 1 plus c sub 2 v sub 2 plus, right? So that's u. And now let me write v. C sub 3 times v sub 1 plus c sub 4 times v sub 2. And now let me just make sure I haven't done anything silly, right? All right. Now, how can we get from where we are now to be able to make the statement that it's closed under addition? Well, let's drop these parentheses and let's group. Let's get the vectors v sub 1s by grouped together, and let's get the v sub 2s grouped together. With me? So now I would have c sub 1 times v sub 1 plus c sub 3 times v sub 1. Right? So I'm going to drop those parentheses and I'm going to just group. Now I'm going to put the parentheses back just so you can, it's clear what I just did. Ready? And now let's do the same thing, except we want the v sub 2s to be grouped together. So c sub 2, v sub 2, plus c sub 4 times v sub 2. All right, and now let's factor out v sub 1. Okay, so if we factor out a v sub 1, we would be left with a scalar, c sub 1, plus another scalar. And then let's factor out a v sub 2, and we would simply be left with a scalar plus another scalar. And now I want you to see that, if you don't mind, follow me, see this little thing right here? Follow me. Look at what we have here. For we are allowed to have H is any scalar attached to v sub 1, correct? It could be a 2, a 3, 0, -3. So do you see how C sub 1 plus C sub 3 is simply just when you add those two scalars, or when you add these two scalars here, it meets the criteria for a linear combination for subspace H. Right? Everything works out perfectly. And you can, so no matter what, if you were to plug some numbers in here for C1, C2, C3, C4, well, you can always add the numbers, and then you would just have a different scalar attached to your vectors, and that's just also part of H. Because what is H? H is every single vector, the sum of every vector, v sub 1, v sub 2, for any scalar. Okay, so we do have closure under addition, the zero vector, for scalar multiplication, right? Closed under scalar multiplication. Well, it's simple. You just need a single vector, right? Well, you could think of it as, I tell you what, you should try this on your own. I think at this stage of the game, you pretty much got the gist, but you would just simply have to show that a scalar attached to a vector would also be in the vector space H. You can go through, you can try it. I've shown you some like this before. It's not that bad at all. What you would find is that you also have closure under scalar multiplication. So the linear combinations that make H, in other words, the span of the two vectors, meets all the criteria to be able to make the statement that yes, H is a subspace. Now, it's not you have to be explicit when you say H is a subspace, right? It's not implied what it's a subspace of. So of what? In this case, V. Right, so what it's a subspace of is important when you make the statement that H is a subspace. I hope that was clear. We are going to continue in for the next section, and I hope you're up for this journey, because now that we have vector spaces and subspaces, we're going to go to null spaces and column spaces, and I'm going to try my best to use my Netflix analogy and push it to its limits until it falls apart, but I will see you there.